Weekly review question 1, since it stopped recording my first one. I have to do it all over again. Okay. Textbook and class notes is what I used. So, first I'm just going to draw some DNA with some adenines and thymines. And then... Ooh, this is... Okay. So now I'm just going to draw a replication fork. I'm just going to use this later, but I cannot talk and draw. I'm simply not that gifted. So... Okay. So... Okay, so to determine the leading and lagging strand, basically what this is a replication fork, and it's being pried apart by helicase. And when it is pried apart by helicase, it is bidirectional, and that just means that it's being read in two directions. So this side is being read this way, and this side of the fork is being read this way. So this is being read to the right, and this is being read to the left. So the template is read from 3 to 5 prime. So from here, because the replication fork is being read to the left on this side, 3 prime will start here, and 5 prime will start here, and then up here will be 3 prime, and right here will be 5 prime. And then again, because this side of the replication fork is being read to the right, this is going to be 3 prime because 5 prime end is right here, and this is going to be 5 prime, and then this is going to be 3 prime, because again 3 and 5, and then this is going to be 5 prime. Okay, so to determine if it is leading and lagging, like I've said multiple times, the replication fork is bidirectional. So the template strand is read from 3 to 5 prime. So on this replication fork, 3 to 5 prime is right here, and 3 to 5 prime is right here. So the synthesis of the replication for the leading strand is continuous. So in that case, it would be 3 to 5 prime right here. It would be the leading strand. Because again, because it is bidirectional, it is being read this way. And there is no running into the replication fork. So therefore, the synthesis is continuous and it's leading strand. This top strand right here, again, being read to the left. 3 to 5 prime is how it's read. So because it is being read from 3 to 5, but it is going in the left direction, we still do have to follow the 3 to 5 prime. So we're going, and then it runs into the replication fork. But again, it's being read to the left, so then we have to come back, making the synthesis discontinuous. So that leads us to concluding that this is the lagging strand because it is being read to the left. Now I'm just going to make it quick, and I'm just going to tell you that this bottom strand is the lagging, and this top is the leading, just for time purposes. But again, if we were to explain it, it's being read to the right. The bottom strand, 3 to 5 prime, it's being read, even though it is being read to the right, it does run into the replication fork, and it does have to go back, making it the lagging strand. And then this one, 3 to 5 prime, it does not have to stop for anything, does not run into the replication fork, therefore it is the leading strand. So, to start with the leading strand, initiator proteins bind to double-stranded DNA, so we're just going to do this. And they like to bind to a lot of adenine-thymine bonds just because it is easier to break that bond because it is a double bond, whereas the guanine and cytosine is a triple bond. So initiator proteins bind to double-stranded DNA, and then helicase comes in and it pries apart the double-stranded DNA, making this beautiful replication fork. And then single-stranded protein, binding proteins bind. I'm just going to draw some circles. We're not using that side, so I'm just going to leave them there. But these are single-stranded proteins that do bind, and that just basically keeps the replication fork open. Apologize. So let's add some nucleotides. A, T, C, G, A, C, T, G, A. Okay. I don't know if that's 10. I really can't count. But I think, I don't even know. I don't care. So, primase is going to begin replication by adding the RNA nucleotides to the strand. So, this would be U, A, G, C, U. So then DNA polymerase is going to come in, and it's going to, oh, you know what? That isn't 5. I'm going to add a C. So then DNA nucleotides are added onto the 3' end of the DNA, which is here. Like if I was looking at it, like this is a C, this is the 3' end, and this is the 5' end. That's what it would look like if it was there. But anyways, so sorry, I'm using my hand. So DNA polymerase is going to come in and it's going to add those nucleotides. So then we got G, A, C, T, G. So then after DNA polymerase does come in and add these nucleotides, RNA primer has to be degraded. So nuclease is going to come in and it's going to degrade all of the RNA nucleotides. And then repair polymerase is going to come in and it's going to replace the RNA nucleotides with DNA nucleotides. So this is going to become a T, A, G, C, T. So then, don't do that. So then after the nucleotides are replaced by repair polymerase, there is a little gap, like right here, that needs to be sealed, and ligase is just going to come in and it's going to seal that. Okay, so then that is for the leading strand. So for the lagging strand, the first 3 steps are the exact same. The initiator protein is going to bind. Double-stranded DNA is pried apart by helicase, and the single-stranded protein binding proteins bind. So then the first Okazaki fragment is started. So what's going to happen with that, it's basically the same as the leading strand. The RNA primer is going to come in, and it's going to add these nucleotides. I'm going to add them over here. So this is going to be C, the RNA nucleotides, I meant to say, the primase. So G, U, A, 1, 2, 3, 4, 5. Okay, what? 1, 2, 3, 4, 5, 6, 7. I'm going to add a C over here so I can do this. Okay. So the primase comes in, and then DNA polymerase comes in. It adds the other DNA nucleotides. G, this is going to be T, this is going to be A. So then it does run into the replication fork. So when it runs into the replication fork, the Okazaki fragment is finished. So I'll just write, this whole piece right here is an Okazaki fragment 1. So then it has to go back in and the RNA, how am I going to explain this? The nucleus has to go back and the RNA primer has to be degraded because you can't leave the RNA nucleotides on. So all of the RNA nucleotides are removed, and that's done by nuclease. And then again, repair polymerase is going to come in and the RNA nucleotides are going to be replaced. So I'm writing it this way just because it's easier for me, but it is read again 3 to 5, so it's supposed to be written this way. Again, just easier for me to write this way. T. Okay, so then after the repair polymerase comes in and replaces this, or actually before I even explain that, where the nucleotides 1, 2, 3, 4, 5, where these nucleotides were replaced, that's the second Okazaki fragment that happens. So then after this comes in, the repair polymerase comes in and replaces the RNA nucleotides with the DNA nucleotides. Then the Okazaki fragment has to be joined together and it has to be sealed, and that is done by ligase. So again, right here is where the primase ends and the DNA nucleotides were added. So this is where the little gap is. So that's where ligase is going to come in and seal it. So again, this whole first one right here was the first Okazaki fragment, and then when the repair polymerase came in, that was the second Okazaki fragment. And that is it.